Hello students, welcome to the Growth and Development MEDI 31031 one credit course offered this semester. I'm Dr. Sadhna, your course coordinator for this course. This entire course comprises of about 15 lectures, one per week, to be held every Monday between 11 and 11:50 a.m. Now, as you know, for this first week we have gone online, but we hope to see you next week in person, and we will keep you updated regarding the arrangements that are going to be made to get you on campus. Okay. So this is a very interesting course where we shall see how we ourselves begin life as a single cell, and in just 9 months that single cell becomes trillions and zillions of cells simply by dividing and hence multiplying, and emerges 9 months later as a laughing, crying, jumping individual. So it will read like a story, and where we stop in one class, we shall continue in the other. Now, today's talk is just an introduction to the science of embryology, where we will learn some new terms which are specific to embryology. And we will also see how development begins even before the zygote is formed. That means how gametes develop, that is, the sperm or the ova develop. So these are the objectives. Looking at terminology, we recall how cell division occurs and what is gametogenesis, and specifically we will begin with spermatogenesis. So as I said, we begin life as a single cell shown here, and then you soon acquire different forms until 9 months later you have human features and are ready to be born. So through this story we undergo different stages of development, and here are some terms coming up then. So you will learn what is meant by a zygote, embryo, fetus, neonate, infant, child, so on. So I mean, you know what a child and adult is, but you will learn these um, meanings of these terms. And we will also learn what are these developmental periods that a single cell that is multiplying, increasing in size, etc., will undergo. So what is human embryology? It basically means the study of prenatal, that means before birth, or intrauterine development of a human being. Remember, development doesn't stop at birth. So basically, firstly, we are dealing with the stages of human development before birth. So it is said that the 6 or 7 great teachers in life are the following: who, what, when, where, how, and why, or sometimes even why not. If we can answer all these questions about anything on earth, you will have known most things. So, pertaining to embryology, similarly, several questions will come up and we can answer them as we go along. So, firstly, what is embryology? So, simply defined, we said study of human development before birth or prenatal development. When does life traditionally begin? So, when we are at the one cell zygote stage. So, you will learn what these terms mean. How did it happen? By the processes of gametogenesis and fertilization. So, we will know details of these. How long does it take? That means how long is our period of growth before birth? So, that is known as the gestation period. So you will know how to calculate it. Where are we developing? So in the mother's womb or inside the uterus. So that period of prenatal development is also known as intrauterine life. And how do we survive before birth in a very special enclosed environment where we are swimming in a sea of fluid? So we are nourished and supported by a special organ called the placenta, which is very essential before birth but useless once we are born. So this is traditionally defined as a feto-maternal organ. We will study its structure, function, etc. Now, during this whole process of development, problems can arise at any stage. So why do problems occur? How do they occur? What are the factors, whether environmental or genetic, harmful factors that can affect a growing embryo or a fetus? So that is known as the science of teratology, and the harmful substances are known as teratogens. So we will be addressing all these issues in stages. Now, all this before birth, the development from a single cell to a fetus which has complete, all its systems and basic tissues in place. The first part is known as general embryology. Then in the second part of embryology, we study embryology by systems. That means you will learn development of specific systems like the cardiovascular, respiratory, etc. Remember, which are all happening at the same time in the developing embryo. So as examples, we will deal with a couple of systems towards the end of this course. So here now we are going to come across some new terms and understand what is meant by them. So when we consider prenatal human development, now you know that is development before birth, we can monitor the growth of the developing structure inside the uterus in weeks or in months. And at certain stages, specific stages, we name that structure specifically, right? So here in the first picture, you can see it's already a multicellular mass. So zygote, remember, is a single cell that is formed after the male and the female gametes have fused at fertilization. So after the zygote soon starts dividing into a multicellular form. Now don't worry about what to call this, but remember, from fertilization up to the first 2 weeks of intrauterine life, that means first 2 weeks of development, is known as the pre-embryonic stage. It begins when? With the formation of the zygote. Up to 2 weeks, it is known as the pre-embryonic stage, where you will just get multicellular, like a mass like that. Now, from the third week onwards, this growing structure is said to have entered the embryonic period, and this structure will be further developing structure will be called the embryo. So between 3rd to 8 weeks of IUL is known as the embryonic period. Remember, you can think of it in months also. So for example, 8 weeks means how much? It means 2 months. Okay. Now this period is also known as the critical period of development or critical period of organogenesis. What does this term mean? Genesis, means to develop or create, and organo means organs. So most of your vital systems and organs start to develop in this period. And as these organ systems are forming, the embryo is very highly at risk or susceptible to any harmful substances. Suppose it's exposed to the mother is exposed to some harmful drugs or chemicals which can cross the placenta and affect the fetus. So these are known as environmental teratogens. So it is in this embryonic period that the embryo can be affected. Hence it is known as the critical period, and birth defects can occur. Now, once the embryo develops more, it enters the fetal period, and then it's called the fetus. So from 9 weeks up to the end of pregnancy, that is up to 9 months, is known as the fetal period, and the growing structure is the fetus. In this period, what happens is already the organ systems have been formed in the embryonic period. So this is a period of great growth and maturation. Okay. Now, harmful things can attack the fetus at any stage, but this is the most critical period in the embryonic stage that the embryo is most susceptible. Okay. Now, another way to monitor the growth, prenatal growth, is by considering the periods in terms of months, and we divide the whole period of pregnancy into 3 months each. So each 3 quarter or 3 month is known as a trimester. So first trimester of pregnancy means first 3 months of pregnancy. Now if you convert it into weeks, it is 1 to 12 weeks. So note that first to 12 weeks in the first trimester includes this 3 to 8 weeks, right? Which is the most critical period of development, we said, which includes this embryonic period. Hence, we say the first trimester also we can say is a critical period, because that includes 3 to 8 weeks, right? The second trimester of development or pregnancy is the next 3 months. That means extends from 13 to 24 weeks. And now the embryo has become a fetus in the second trimester. So it's a period of growth. And the third trimester is the last 3 months, that is from 25 to roughly 36, 38 weeks. And this is also known as the period of maturation, and it is also the fetus, right? So second and third trimesters, you already have the fetal period, and first trimester includes the embryonic and the pre-embryonic period. Okay, so these are just terms that we use to monitor fetal growth. Now remember, just to highlight the fact that growth does not stop after birth, otherwise you wouldn't be how you are just now. So when you were born, obviously your weight was different, size was different, everything was different. So a newborn is known as a neonate. Up to how much time? Up to 1 month after birth, we call the baby a neonate. Now, up to 1 year after birth, we call it an infant. That means neonate is part of infancy period, right? Because 1 month is anyway part of 1 year. But specifically, infant is known up to 1 year. And then, of course, childhood between infancy and puberty. And you know that there is a pre-pubertal hormonal growth spurt and changes occur in your body. And then puberty is different in males and females, begins a little earlier in females and continues up to 16 to 20 years. So this is a big range. Of course, it will end earlier in females and a little later in males. And then the adult stage is considered at 18 years onwards, and all ossification and growth complete by 21 to 25 years. So even now, some of you may have unossified bones in the body. Ossification is going on. Okay. So to further learn some terminology, now in gross anatomy, you've already learned what are these actual planes, axes, etc. Similarly, we can take sections of the embryo in a sagittal plane or a coronal plane, or sagittal would be like this, dividing into right and left halves. Coronal will be like this, dividing into front and back halves, or transverse sections, etc., to study what's happening inside the embryo. And specifically in relation to the embryo, again, we refer to cranial or rostral means towards the head end of the growing embryo. Caudal means towards the tail end or the bottom of the growing embryo. Now, anterior means ventral, and dorsal means posterior. Okay. So these are specific terms which we use to describe any position of any organ or structure within the embryo in relation to each other. Now, there are some terms used specifically for the embryo to measure the dimensions of the growing embryo. For example, there's something called the CR length or crown rump length. Rump means, see, because the embryo is folded like that, highly folded. Rump means the lowest part of the bottom, or where the coccyx is, and crown is the highest part of the skull. So this is a very good measure to assess maturity of the growing fetus. Similarly, there's another measure known as the crown heel length. When the embryo straightens, the fetus straightens out a bit, then you can measure that. All this is measured by ultrasound. Okay, so these are some terms used. Now, here we come across some more terminology. Now, we will be studying each process in detail. So again, it will be defined, but it's just to expose you to these terms. So fertilization, we'll be studying how a sperm and an ovum fuse. Then it is said to fertilization is said to have occurred and a zygote is formed. Cleavage means cell division. So we'll see what happens. Implantation means that growing structure, cellular mass, sticks to the uterine wall and gets buried inside. So how it implants. Morula, blastocyst, these are again names for the growing structure after fertilization. Blastocyst, morula means a cellular mass. Blastocyst means when it starts developing a cavity inside. Bilaminar and trilaminar germ disc means the further development of the embryo, where it is a two-layered structure and then it becomes a three-layered structure. by the process of gastrulation. Gastrulation means a bilaminar embryonic disc becomes a trilaminar or three-layered embryonic disc when the basic tissues are developing. And neurulation means development of the neural tube, which will give rise to the brain. Now, in this picture, just to give you an idea of the size, you see there's an embryo which had aborted. So before that, what is abortus and what is conceptus? Conceptus means all products of conception or pregnancy, which includes the growing embryo, the supporting placenta, the membranes or the fluid, whatever is formed. Okay. Now, abortus means all products of conception, that means all pregnancy products, if they are expelled or removed from the uterus before full term of pregnancy due to whatever causes it, may be accident, illness, trauma, or even medically terminated pregnancy, then all this, uh, the tissues coming out is known as an abortus. So here is an embryo which is aborted. So we can say it's an abortus also. And the lower picture shows one embryo which has implanted not in the uterine cavity but in the uterine tube. Obviously, it won't last there and the uterine tube will burst, right? So it was aborted and you got that abortion occurred or the embryo got aborted. Okay. So we are going to study human development, as I said, as a continuous story, as a continuous process. And when does it begin? So, when an oocyte or an ovum from a female is fertilized by a sperm. So, if you look at the pictures, doesn't it read like a story? You start like a single cell and then pre-embryo, embryo, fetus, etc. Okay. So, what does this journey involve? It's a very, very dynamic process. Obviously, first it involves cell division, and by dividing cells, you multiply those cells, correct? The cells become many. In fact, hundreds and thousands and billions and zillions of cells finally. These cells don't remain in one place, they migrate to different areas within the embryo, and somewhere they develop more, somewhere they undergo programmed cell death. We'll see how that is essential also. And do they remain the same type? No. So you get histodifferentiation of tissues. You've learned basic tissues in the body. How many basic tissues are there? You remember epithelium, connective tissue, etc. So they differentiate. Then they grow. So organs develop, they grow. These cells get rearranged within the body, and all these processes hence will transform the zygote from a single cell into a highly specialized multicellular human being capable of laughing, crying, running, jumping, so on, and studying medicine. So, how long does this period take? It is known as the period of gestation or the period of total pregnancy. And this is calculated as, now, exact time of fertilization is very difficult to find out. So, it is usually calculated as 280 days or 40 weeks because it's a lunar month for 28-day cycle. So, 40 weeks from the first day of the last menstrual period. So, once a woman becomes pregnant, the menstrual cycles stop. So, when was the last LMP or the last menstrual period for that woman, and what was the first day of that last menstrual period, and from there you can count 280 days. We'll come back to it when we are again looking at fetal period and all that. Don't worry. So you can count this in women with usually regular menstrual cycles. Now, a menstrual cycle doesn't precisely have to be a 28-day cycle. It's always a range. We'll be studying about this. So between 28 to 35 days is usually considered normal, provided it occurs cyclically. Okay. So where does all this occur? So gametogenesis or the process of sperm and ovum formation will obviously take place in the gonads. So you've done structure function and your ITA. So you know that sperm formation occurs in the testes and the oogenesis will occur in the ovaries, and the parts of the reproductive tract are as seen here. So how do we define gametogenesis then? Gametogenesis is the process of formation of male and female gametes. This can be divided as or considered as spermatogenesis, which is the formation of a mature sperm, and oogenesis is the formation of a mature ovum. So we are going to study them, learn about them separately. But before we do that, we must recapitulate our cell division processes because they are important to understand gametogenesis. So we can compare and contrast them, etc. And we'll see how the chromosome number is distributed and look at some abnormal conditions that may happen. Okay. So before we look at gametogenesis in particular, let us recall briefly the cell cycle because mitotic and meiotic divisions are an integral part of the process of gametogenesis. So you know all this. It's just a review. So in any uh, uh, lifespan of a cell, it undergoes various phases, as you can see. So G1, and then you look at this S phase, which is known as the phase of synthesis or replication of DNA. And then interphase means it's in a resting state. Then G2 phase means it's just preparing to divide. And here is the phase of cell division, mitosis or meiosis, right? So cells keep on undergoing uh, these cycles, all cells in the body except neurons. Okay. So it's important to understand that just before a cell begins to divide, it has already replicated its DNA. Now, normal DNA in a cell is defined as 2n, where n is haploid, right? 23 number of chromosomes. 2n means 46 chromosomes containing DNA. So, point is that before it enters, before it begins to divide, it has to undergo the S phase where the DNA doubles in amount. That means we already have 2n DNA. So before cell division, remember, DNA becomes tetraploid or 4n in the S phase. Keep this in mind. But the chromosome number is 2n or diploid or 46 in a normal undividing cell. So within those 46 chromosomes, the DNA is becoming double, 4n instead of 2n before a cell divides. So if you recall mitosis, you remember these phases. We are not going to go into much detail, but just again remember that in interphase, before it enters cell division, the DNA has become 2n has become 4n. That's why the chromosomes become thicker and double-stranded, joined together by the centromere. Now, in a simple mitotic division, you can see how they're moving apart and then they are splitting at the centromere and then each cell and so on, cytoplasmic division. So at the end of this division, you get two genetically identical daughter cells. The chromosome number remains the same. And the DNA, which had quadrupled, become 4n, becomes 2n again in each of this, right? So this is simple mitotic division. Now in meiosis, what happens? Here is one cell. Remember, DNA replicates, so it becomes 4n. And then in meiosis 1, this is the reduction division happening. You can see some material has been exchanged also. So genetic recombination has taken place. So what is the chromosome number at the end of meiosis 1? It becomes 23. But what happens to the DNA? Remember, the DNA from 2n was 4n, right? That's why they become so thick here. So here, at the end of meiosis 1, the chromosome number has become 23, but the DNA is still from 4n, it has come to 2n. That's why you have meiosis 2. Now this is like mitosis, where the cells again split, the centromere splits, and then you get 4 daughter cells. Now at the end of meiosis 2, the DNA also has become half. Do you understand? So here we began with 4n, here it became 2n, and finally it becomes n. But the chromosome, because it's like meiosis 2 is like mitosis, so we get the same number, or 23 chromosomes. So each double stranded becomes each single chromosome in 4 cells. So at the end of the meiosis 2, we have cells with half the amount of DNA, that means N, and half the number of chromosomes, that is N is equal to 23. This is what happens in gametes. So each gamete would have half the amount of DNA and half the number of chromosomes. So that when it combines with the other gamete at fertilization, the normal human chromosome number and DNA is restored. Do you get this? So this is again just to recapitulate about chromosomes. So remember, each set of 23 chromosomes, which are numbered as 1 to 22 autosomes, and then either X or Y or X and X sex chromosomes, right? So 1 to 22 are known as autosomes, the other two are sex chromosomes. So in a male embryo or in a male, human being, you'll get what is the karyotype is known as 46XY, and a female karyotype is 46XX, where you have 22 pairs of autosomes arranged in decreasing order of size and then a pair of sex chromosomes, right? So our human chromosome number is diploid or 2n. Now, in a gamete, obviously a female gamete, because a female has two X chromosomes. So at the end of gametogenesis or oogenesis, when we get four gametes, each one will have only X and X. A female can contribute only X chromosome, whereas a male can contribute an X or a Y chromosome. So what is the significance of this? We will understand later. Okay? So finally, because of mitosis and meiosis 1, gametes have half the number, that means haploid number of chromosomes, and half the amount of DNA coming from either the female or the male. At fertilization, what happens? A normal order is restored. That means 2n number of chromosomes and 2n amount of DNA. Okay, so that's why we had to understand mitosis and meiosis first. So where is this spermatogenesis, oogenesis going to take place? Here you can see in the testes, and this is in the ovaries. So we're going to understand these processes separately. Let's start with spermatogenesis. So again, to answer those questions, remember who, what, when, where, how, why, etc. So where and when does this story begin? Now for both, either spermatogenesis or oogenesis, the story begins very early on when you yourself are an embryo. Imagine you are in your second week of intrauterine life. Okay, in fact, a pre-embryonic stage. So you are like this. Now don't worry about what all this is. You don't worry about what is epiblast. So it's one germ layer. But there are some cells that break off from this epiblast layer, and they are early cells. So they are known as primordial germ cells. They break off, okay, and they move to something known as the yolk sac. So this big balloon like structure, this is the growing, this is you at 2 weeks, and you have a big balloon in front of you that's known as the yolk sac, which is filled with some material. So the wall of the yolk sac, this is the wall shown here. So these primordial germ cells migrate into the wall of the yolk sac and stay there. And then in this fourth week of human development, now you are in the embryonic period, the PGCs or the primordial germ cells will migrate inside the embryo like that to the developing, and they will, which is somewhere where your kidneys are right now in your lumbar region. So there they will induce or stimulate the development of the gonads, the testes or the ovaries. That means actually they're as if they are creating a house for themselves, because here there is only tissue, some basic tissue here. So in that tissue they will create a gonad. They will stimulate development of a testes or an ovary, and then they will reside there in the growing. So these are the cells, and they will migrate there. This is a cross section of the embryo. They will migrate, and here they will form, there's something called the genital ridge, where the gonads will form, whether a testes or an ovary, and they will undergo gametogenesis in these gonads. So spermatogenesis or oogenesis. So that's how early, even when you are an embryo, your primordial germ cells are making your gonads and starting to develop. Okay. So let's see about spermatogenesis specifically now. Now, these primordial germ cells have come. Now, this is a testes of, say, fetus or a newborn. The primordial germ cells are lying quiet in the testes, okay? And they lie quiet like this until puberty. They do nothing in the male. So just before puberty, because hormones, testosterone, etc., start to be producing, pituitary starts producing some hormones. And what happens to them then? The seminiferous tubule, the testes themselves mature further. You get hollow seminiferous tubules are forming, within which the primordial germ cells now begin to change and begin to form the next stage of development, that is known as spermatogonia. And there are two types, type A and type B. How? By simple mitotic division. So we started, say, with one cell like that, one cell like that, some cells, and now each cell, can you understand, will divide multiple times and give rise to spermatogonia, which will lodge in the seminiferous tubules, which have acquired a lumen. So at the same time, testes also maturing and these cells are changing shape, all under the influence of hormones. So let's see, spermatogenesis as a process can be studied by dividing it into three phases. First phase is known as the phase of spermatocytogenesis, whereby spermatogonia further now are going to form something known as primary spermatocytes. We'll understand this in detail soon. Now here just look at the phases. The next phase is known as the phase of meiosis 1 and meiosis 2, or the phase of cell division, where a primary spermatocyte is going to divide to become two secondary spermatocytes. And in meiosis 2, each secondary spermatocyte is going to form two spermatids. These are spermatids. So in this phase, this whole phase, see, you can see one primary spermatocyte has formed four spermatids. We'll understand about uh, chromosome number also. Do you remember chromosome number was 2n when we started? But remember that DNA becomes 4n and then it's going to divide. So we will understand this better later. Here, let's just understand this whole phase. So first phase was of spermatocytogenesis, where a primary spermatocyte is formed. The second phase is meiosis 1 and 2, where you get two secondary and then four spermatid cells being formed. And the third and final phase is known as spermiogenesis, which is a period of great change where a spermatid is going to transform. Remember, no more divisions. It's going to transform into a mature sperm. Okay, so let's understand this step by step. So in this first phase, as I said, remember we started with primordial germ cells. And at puberty in the male, they start undergo simple mitotic division to give you spermatogonia. See, so this cell is a spermatogonium. Now, there are type A and type B. Okay. But no matter what type, so approximately half are A and B. But before they go further, all type A will change to type B, which is type B will remain same, but all A also change to type B. So finally it is a type B spermatogonium. It's a large cell, okay, with having diploid number of chromosomes and 4n tetraploid DNA. Now what happens next? So this is the stage of spermatocytogenesis. So this spermatogonium type B will now enlarge by growth. It doesn't divide, it enlarges by growth and differentiation. So changes in some structure to form primary spermatocyte. Okay. So what is the chromosome number again in this? It's diploid, and remember tetraploid DNA, because DNA has been doubled before the cell enters cell division. Okay. Now we move on to this phase. So now we have a primary spermatocyte, and in meiosis 1 then there is reduction division. So chromosomes move apart, and each secondary spermatocyte then contains haploid number of chromosomes, right? N is 23. But what about the DNA? So it will contain 2N DNA. Remember, the chromosomes are thick and double stranded. They have just moved apart, because here there was tetraploid DNA. Remember that? So half N number of chromosomes, but still 2N number of DNA. That's why we need meiosis 2, so that even the DNA is halved. Is that okay? So the cell, the secondary spermatocyte, soon starts dividing, and now each double-stranded chromosome will break. The centromere will split, and then each chromosome becomes single-stranded and gets divided into this. That's why into the spermatids. And here then you see that each spermatid now will have n number of chromosomes, that is half, and n amount of DNA, which is half. Okay, now it's ready to form the sperm. So that's why we have meiosis 1 and meiosis 2. Now through all this, note also the cytoplasmic division. Is it equal or unequal? So it is equal so far, correct? Now we'll see about the third phase. So this is still a word about meiosis 2. The secondary spermatocyte dividing to form the spermatids. It's a very rapid division. And now at the end of this, 4. So from one primary spermatocyte, here we get 4 spermatids. And each one will have N23 chromosomes and haploid amount of DNA. That means half a normal cell. Now let's look at this last phase. So this is the testes where it's all occurring. So from periphery, so this is a seminiferous tubule. The cells, as they change shape and divide, they move from periphery towards the center, like this, towards the lumen. Okay. So this is the last phase of spermatogenesis, known as spermiogenesis. How can we define it? It's a series of changes in a spermatid resulting in transformation of the spermatid into spermatozoa, or a mature sperm. So it's a period of great change, no more cell divisions. So let's look at the change. Let's understand from the figure. Now here you can see this is a round cell called spermatid. Slowly it is changing shape and a tail is growing out of it, right? So what are the changes? Here is the nucleus containing the DNA. So the nucleus of the spermatid finally is going to become the head of a mature sperm. See, the head. It's going to become like a rocket or a missile. So the head contains all the genetic material. You know, the cell organelles have also been formed in the cytoplasm. So the Golgi apparatus is going to form, you can see the red structure forming there, like a cap. Or here, this is the acrosomal cap, like a cap sitting on the head. And this is important because it contains a lot of, it's not only a protective layer over the head, but it contains a lot of digestive enzymes, acrosomal enzymes. We'll understand why later during fertilization process. Now mitochondria, mitochondria provide energy, or energy powerhouse of a cell. So they are very essential to the sperm because it needs to be very motile. So the mitochondria rearrange themselves around the neck of the sperm. So mitochondrial sheath is formed just below the head. Okay? And it's going to provide the energy that a sperm needs to move. Now, you have centrioles also in the cytoplasm. So the proximal centriole starts growing like this into an axoneme, and you get a head, neck, middle piece, and tail. So the neck, middle piece, and tail are formed from the axoneme, and around the neck you have the mitochondrial sheath being aligned there. Okay, so you get a sperm looking like that or looking like that. Notice something else also happening. See the cytoplasm? While the organelles are getting aligned and remaining to do what they have to, but there is some excess cytoplasm, see, being shed off. It is just removed. It breaks. Sorry. And this is known as Raynaud's body. So why is the excess cytoplasm shed off? It's like shedding off excess baggage, because this sperm needs to be as fast as a rocket. It needs to swim like an Olympic swimmer against the tide. Hence, it needs tremendous energy but less baggage. So it retains only the essentials in the form of the genetic material and the organelle that it needs to survive and support it, and a very powerful tail or a flagellum like tail which will help it swim. So it's slim, fast, and extremely strong and energetic and mobile. And this is a picture showing you the many sperms that are formed. Okay, so this process is known as spermiogenesis. So where has all this been happening? We've learned about spermatogenesis and its three phases. So here is a microscopic histology picture of the testes. You can see the capsule, and here these are the cut cross sections of seminiferous tubules. So there are many seminiferous tubules, they are hollow tubules, and the cells are present in each tubule. The dividing cells are, as oriented as if the earlier the somatogonia, etc., will be found here. And as they mature into primary spermatocytes, then secondary, and then spermatids, and then the sperms. So the sperms are usually found, if you look at this spermatogonia, see, the larger cells will be primary spermatocytes, secondary, and then they move like this towards the lumen. And here are the spermatids forming the sperms. So the sperms remain in the lumen, and they are attached to something known as nursemaid cells or the Sertoli cells. You may have heard of Sertoli cells. We will be doing histology, then you know more about them. They have varied functions. They're unique cells in the sense they protect these growing cells. They're scattered in between these growing cells like that, tall columnar cylindrical cells like that, and they protect them in a unique environment by having lateral kind of arms extending out to from one Sertoli cell to the other. So suppose there's a cell in between here, and it will protect this cell, and then the arm will break, then again the arms will rejoin here between two adjacent cells. So each growing cell is very well protected until they become sperms. So they provide nourishment, they protect. Okay, they have varied functions. We'll learn about them later. So this process itself, this entire process, is very well controlled, by hormones. Mainly which hormone? That is the testosterone. And where is that produced? Of course, it is another influence of ICSH, or interstitial cell stimulating hormone, secreted by the pituitary, LH or ICSH and FSH. So those hormones stimulate these cells in between the seminiferous tubules. These are known as interstitial cells of Leydig. These produce testosterone, which then stimulates spermatogenesis within the seminiferous tubules. Right? So it's very precisely controlled, as you can see, both time wise and also how these cells differentiate. This is a high power picture of one seminiferous tubule, another one. Here are the interstitial cells. You can see they are outside the seminiferous tubules, and these are the cells dividing. See, you can see the mitotic figures also. Chromosome figures can be made out. Chromosomes moving apart, and then you have the sperms attached by the heads to the Sertoli cells. They will stay in the seminiferous tubules because they are still immature, and then finally they mature in the epididymis. Then they are ready to be ejaculated. Okay, so it's a very precisely controlled process. For your interest, find out what is blood testes barrier. So assignment or self quiz: what is blood testes barrier? You've heard of many barriers in the body. So find out what is blood testis barrier and its importance in spermatogenesis. So here is a summary. Basic facts. When does it begin? Now you can answer, no? Who, what, where, how, why. All right. So spermatogenesis actually begins at puberty because the spermatogonia have been quiet. The primordial germ cells have been quiet at birth, and they only become spermatogonia at puberty. Okay. But once it begins, then it continues throughout life. That means even an 80-year-old or a 90-year-old can produce sperms. So males are lucky that way. Now, if you look at the process, we've seen one primary spermatocyte give rise to four mature sperms because of the process. Now, how much does one cycle of spermatogenesis take place? That means from the time when a spermatogonium becomes a primary spermatocyte and so on till a mature sperm, it ranges about 64 to 74 days. Meanwhile, it's not like all others will stop. So one set starts like this, then second set has started. So every so many days, more and more sperms are produced. Now, daily, how many million? I don't know who counted them, but they are approximately, obviously they counted them, 3 million sperms are produced daily. Now, but you should understand that what is the normal sperm count means. It is counted as 300 to 6 million sperms per ejaculate. That means whatever is coming out of the urethra, right? That is up to usually 3 ml amount, and that 3 ml contains about 300 to 600 million. So per ml you can calculate. All right. So that's the normal sperm count, because you need to investigate sometimes in cases of infertility, even the male sperm count. So when is a male labeled sterile? Now we have to be very careful when you label a man sterile only after proper investigations. So usually it's found that if per ml, if per ml of seminal, of semen fluid contains less than 20 million sperms per ml, or it will be 60 million per ejaculate. So this is normally the sperm count. If it's 20 million per ml, then this man may be, having fertility issues. Also remember, it's not only the sperm count, but as we shall see at the end of the next lecture, when we see abnormal gametes, the sperm structure also must be normal. So example, if the sperm count is normal but it's a two-headed sperm or a two-tailed sperm or a short tail, long tail, etc., deformed sperm, even then it may not be able to fertilize. Now, how is this whole process regulated? We said it's by testosterone, which is produced locally in the testes by the interstitial cells of Leydig. And how are these stimulated? These are stimulated by the pituitary hormones known as ICSH, interstitial cell stimulating hormone, and FSH. So LH is in the female, ICSH male, and FSH is there. Okay. So finally, again, this just recapitulates all about the DNA and all. Read, we've already done this. But finally, at the end of spermatogenesis, we have sperms. What is their genetic constitution? So all will have 22 autosomes, but half of them, so half, two of them will have 22 plus X number of chromosomes. The other two will have 22 plus Y, because what was the original karyotype in a male was 22XY. So half will contain X chromosome, half will contain Y, besides the 22 autosomes. Okay. So finally, this is an important point to remember, who determines the sex of the embryo or the child at fertilization? See, so if an egg-bearing sperm fertilizes an ovum, which can give only X, right? So the embryo will have XX as the genetic sex. In that case, it will be a female embryo. But if a Y-bearing sperm fertilizes an ovum, what will be the genetic constitution of the resulting embryo? It will be XY, right? 22 plus XY. In that case, it will be a male embryo. So who determines the sex of the child? It is always the father, because the woman cannot contribute a Y chromosome. So please educate the community, because I know in many cultures, a man wants to marry second time or a third time if he has, say, 6 daughters by the first wife. saying that, oh, you have not given me a son, so I'm going to marry again. But remember, who determines the sex of the child? It's the father, because he can contribute two different sex chromosomes. All right. So these are just for you to read why we are going to study the science of embryology, its clinical, relevance and all, just for your general knowledge. And lastly, now with when we study in detail all the processes going on, we will realize that we are, each one of us, born normal is really a miracle, God's miracle, life's miracle. And so many things could have gone wrong along the way, but in most of us, they didn't. So where they go wrong, like in this fetus we had received in the Department of Anatomy in another college where I work, you can see how deformed it is. The organs are coming out of the abdomen. Obviously, this won't survive. So when we get such defective babies or fetuses stillborn, then we can use them. We can, I mean, study them with humility and to find out where and what possibly could have gone wrong, so we can learn lessons. So this saying hence is very, very pertinent. Nowhere does nature reveal her mysterious, miraculous, myriad means varied, mysterious, miraculous workings than when she deviates from the normal path. That means only when we come across something abnormal do we appreciate what is normal, right? So, hope this introductory lecture was useful, and I certainly hope you enjoy the course for its own sake, not only because it's a one credit course that you must pass, right? Because you're learning so much about yourself. Thank you for now. This will be uploaded soon.